Welcome to the Evolution 2.0 podcast. Perry Marshall here. In this episode, we are talking to Johnjoe McFadden about his books Life is Simple and Quantum Evolution. He is a professor of molecular genetics at the University of Surrey, and he has written a number of popular books. Very talented writer, and especially his history of Occam's Razor is quite interesting. Let's join the interview now. So, Johnjoe,
yep.
Nice to meet you. I'm sure I've known who you are for at least 10, maybe 15 years. It's an honor. It's a pleasure. I was looking at your Wikipedia page. You're from Donegal, right?
That's right. Yes. Yeah. From the northwest of Ireland.
Where in Donegal?
Well, I was born at a place called Fulcarra, which is right on the coast. It's a port, a very pretty little harbour, and I was born there. But
west of Dunfanaghy?
Yeah, it's right on the coast, so you can't get any further west at that latitude, if you like, because it's the next west is the ocean. So it's as west as you can go at that latitude, and yeah, it's in the Gaeltacht area where many of the people speak Irish.
I am almost sorry.
I only lived there for the first 4 or 5 years of my life before my family migrated to England. So that's why I don't have an Irish accent.
Okay. Well, I was just very close to there in November.
Okay.
I was up in Dunfanaghy, and there's a little corner called Brinlac that I went hiking through, and there's lots of turf and peat, like places where they harvest that, and it was very beautiful. So it was a great little bit of vacation time. I love Ireland. So
it is very beautiful, very, very kind of rugged and lonely, and kind of a little bit magical, the area around there. I think there's a certain wistfulness about it with the abandoned cottages and countryside that's just hills and mountains and lakes and beaches. It's very, very beautiful.
Well, I'm really glad to have you here. I've probably got about 35 minutes or so, and what I was thinking about doing was I'd like to talk about both of your books, and I'd like to talk about at least enough of your history to get an idea of why you would get the burn to write books like this, because these are very, very thoroughly researched books. Like, I can tell you must have read like 40 books in order to write this one book. I mean, this is the level of detail on a whole range of topics is really impressive. So I just figured, well, here we go. Anything you want me to know before we jump in?
No, I can give you a summary of why I write them, because I'm really interested in these topics, the topics of whether quantum mechanics is involved in biology. And I came to an interest in Occam's Razor when I was a colleague of mine. Mostly my university work, if you like, my paid job is not to do quantum. Well, actually, it is to do quantum biology now. I'm now a director of a quantum biology doctoral training center at the University of Surrey. But still, mostly I work in molecular genetics of microbes and an area called systems biology, which is a kind of intersection between biology and the mathematics, where you build mathematical models of biological systems in the aim to gain a greater understanding, and also to be able to predict what they do more accurately. And a colleague of mine from Amsterdam came and gave a talk which was entitled Occam's Razor has no place in biology. And His argument was that biology is irreducibly complex. In other words, you can't simplify it. It's something that you have to swallow the whole lot, not try to dissect it. So the reductionist approach that has been so successful in other disciplines shouldn't be applied in biology. Because Occam, I knew very little about Occam's Razor, but I did know there was this place called Occam on my drive to work. And I thought, okay, I'll find out a little bit more about it. And I found out that evening I was giving a talk the next day, so I wanted to answer Hans Westerhoff is the Dutch guy. I wanted to answer his talk. So I did a bit of research and digging into Occam's Razor and found out, for example, that it is named after the village of Occam, and particularly one of the sons of the village of Occam, William of Occam, who was a 12th, 13th century friar, Franciscan friar, who went to Oxford to study theology, then called the Queen of Sciences. There you go, Queen of Sciences. That would intrigue me. What? Theology, science? So I was intrigued. And then I learned that Occam kind of did some fairly radical things for his time, in that, for example, a generation before him, Aquinas, Thomas Aquinas, the famous Italian theologian, had kind of fused theology with Aristotelian science. This was the age of beginning of the age of the Renaissance, the first glimmerings of the Renaissance, which a lot of Arabic translations of Greek works were coming into Western Europe and ignited a thirst for science, particularly Aristotle's science. And Thomas Aquinas enthusiastically imported Aristotelian science into Christian theology, and he used it to provide 5 proofs of God, and they were pretty much accepted at the time. And Occam came along a generation later and says, no, they're all wrong. They're all wrong. None of them work. And I thought that was pretty radical for a Franciscan friar to say that these proofs of God didn't work. And he went on to argue that for that reason, that God's non-provable, essentially. You can't prove God is the matter of faith. He said science and religion are completely separate and should not be mixed. He is, I believe, the first person in the history of the world. I've said this several times, and I keep expecting someone will say, no, you're wrong. Somebody else got this earlier. But he is, I believe, the first person in the history of the world to make a clear distinction between science and theology. And all of the Western world depends on that distinction. Ultimately, that is where secularism has built the Western world, where we've divorced religion from science and allowed science to develop, even though it has bizarre things that are not really allowed in the Christian world. And although there's been many setbacks, such as Galileo's trial, that approach has triumphed and it has changed the world hugely. And the first person to make that step was William of Occam, and no one even knows who he is, at least at that time, and still probably most people don't know who he is. But he's most famous for his razor, because his logic that he developed alongside the disproofs of God was to make life simple, to make explanations simple. So if you have a bunch of explanations for something, get rid of any of those which have extraneous entities that you don't need. Make this, go with the simplest explanation if it works. Obviously, if it doesn't work, you've got to go for the next simplest and then the next simplest. And in that way, you can explain any complex things, but you explain it with the simplest possible explanation. So that's called Occam's Razor, after William of Occam kind of destroyed medieval metaphysics with its razor. And of course, he was then accused of heresy, went to Avignon to face trial in front of the Pope, ended up accusing the Pope of heresy and having to flee Avignon, chased by a posse of papal soldiers. So he was an interesting guy. And I thought, wow, nobody knows about him. And I thought, wow, people ought to know about him. Anyway, I answered Hans's talk the next day, giving a little bit of history on William of Occam. And I was hooked. I thought, wow, this is an interesting question, simplicity in science. And it hasn't been explored really how important simplicity is for science. So I thought I could give it a crack in a book. Now, shall I withdraw? No, don't have blinds here. Big window here, and it's shining in on me. But I realised I don't have blinds in that window, so we'll just have to put up with it. Is that okay? Can you still see me okay?
Yeah, I can see okay. So
Good.
what's ironic and fascinating to me is this didn't keep Occam from being a Franciscan friar or from believing in God. He just felt like science needed to speak for itself, nature needed to speak for itself, rather than getting mixed with all kinds of Platonic ideas about seedness or cherryness or fatherness or motherness or rockness. And I don't know, that's probably getting us a little far afield, but you were hooked.
I was hooked.
Was it
just kept pulling on this string of simplicity and science and William of Occam and his work, and it just kept on coming up, pulling in lots more interesting fish from the ocean of information about this. And and I thought, well, a book needs to be written, and I'm the man to write it. So I gave it a bash.
Well, simplicity is very, very hard work.
It is. Simplicity isn't as easy, isn't as simple as you might think. It's difficult to define, but it's one of those things that, although difficult to define, it's a bit, as they say about a famous American lawyer or lawmaker, I can't remember who he was, said about pornography that I can't define it, but I know it when I see it. And I think simplicity is a bit like that we know it when we see it. We admire simplicity in explanations, but also in art, in music, and it kind of shines through. If people have simple ideas, they're they're clearer, they're more convincible, and you can convince people more easily with a simple idea. But many people are hooked these days on highly complex ideas, what we call pseudoscience and conspiracy theories, and they build lots and lots of levels of explanation, and they can explain everything. And that's another kind of shock to me. One of the reasons I came into thinking about simplicity is I found that when I was arguing with a creationist about that evolution is the only way you can explain the world, the biological world, and I thought I could easily defend myself and convince someone who was intelligent, and this guy was intelligent, but everything I threw at him, he had a contrary explanation for. So, well, there's a fossil record, and I said, well, that's not a fossil record. That's not only a few thousand years old. It's Noah's flood, and all these creatures got buried, and that's what you're seeing. And I said, well, what about the layering of the fossils in different layers? And I said, oh, that's easy. A hydraulic sorting. It's how different objects will get sorted according to their size and density, and you'll get this kind of layers. Or what about the fact that, for example, if you say that this flood happened 2000 BC or something around that, that's when the Egyptians were building pyramids and writing hieroglyphs of all of their adventures and their conquests, and they didn't mention the fact that their pyramids were under a mile of water for many years. That seemed to have got out. And he said, "Oh, you don't believe in carbon-13 dating, do you?" And it just went on, and I realized that if you have someone who's sufficiently creative, they can convince themselves of anything. They can convince themselves that Elvis is living on the moon, that Donald Trump won the last election, and all of these things. If you allow as many layers of explanation as you like, and the only way of dealing with that isn't, as I had previously thought, through logic, because that guy was logical. Everything he said made sense, but there was just a mountain of it. And I realized, actually, at the end of the day, you can't disprove people, but you can say there's this mountain of improbable things that you are claiming on one side, or there's a really simple explanation, natural selection. Which do you prove? Which do you go with? And science ultimately says, well, go with the simplest. And that was what William Occam discovered, and has driven science ever since. And I think it's still the fundamental principle of science.
Well, there's a famous quote, I forget who it's by, but it's something like, I prefer the simplicity on the far side of complexity. Like you start out seeking something simple, the whole endeavor becomes almost impossibly complicated, but then it becomes simple again at the end. Like even something like learning to play the guitar or the piano. When you're in the steepest part of the learning curve, it just seems like there's more things than you could possibly comprehend. But at some point, it comes back again, and then you're just strumming a guitar. And not really very hard, because there's just these certain things that you learn the muscle memory. I find this principle of simplicity, it applies to product design. Like a kid has to be 6 or 8 years old at least to use a Windows machine, but a 2.5-year-old can use an iPad. Because Steve,
the Apple Mac,
a huge amount of complexity out of it at great effort. It took an enormous amount of ingenuity to figure out how to bury all that complexity and hide it. It's still, the two are just as complex as each other. They're both incredibly complex devices, but the iPad has been reduced to something a 2-year-old can play video.
I agree. And when I first started using computers, when MS-DOS came out, it was horrible. It was really horrible to use. And then Apple said, "Hey, you can have a mouse and you can just move things around and press buttons." And it was that simplicity that we greatly admire in design. And I think much of the modern world is crafted around simplicity in terms of design, like the Apple Mac, and modern architecture is all about simple lines. Modern literature is kind of stripped away a lot of the florid language of the 19th century and early 20th century, and stripped away to very lean prose. Modern music, Michael Nyman and Philip Glass and people like that, stripped music down to simple ideas and simple ways of putting music together. But of course, many people like the more florid stuff, the more complex, the more baroque paintings or music, etc. There's nothing wrong with that. But I think the general drift of modern Western culture has been towards simplicity.
Let's talk about your quantum evolution book. I've had this for quite a while. The reason we ended up getting hooked up was I cited your book in a paper that I wrote recently, and you tweeted it, and I saw that, and then we started talking. But as far as I can tell, this is one of the most popular books on quantum biology, and maybe one of the early ones. Is that at all correct?
The only one earlier is Erwin Schrödinger's What is Life?
Well, yeah, that's a whole different.
Yes,
that's a whole different.
Indeed, it's a very different book. It's a very different time. Who wrote it in the 1940s, mid-40s, I think. And I think mine was the first book on quantum biology since that. Of course, I don't know if you've seen it, but Jim Al-Khalili and I wrote another book on quantum biology, published in 2015, I think, called Life on the Edge, which is a kind of update on quantum biology.
I very likely do have it, but I hadn't pulled it. So why don't you help us understand why you felt like quantum biology needed to be pushed to the front of the line? Because I know an awful lot of biologists that really would prefer not to touch the quantum stuff. They just
absolutely
let's stick with
absolutely. As I was trained as a biologist, and basically as a biologist, you You've heard about quantum mechanics, but basically you then forget about it. If you might have a physics course somewhere along the line that you might look at solving Schrodinger's equation for solving the hydrogen atom, but you don't really understand it. I mean, biologists have often, including me, fled the physical sciences because we don't like the maths. And physics is, of course, deep maths. So we prefer thinking in pictures and narratives. And we have taken on the idea that life is complex, even as Hans was saying, irreducibly complex. And biology is kind of anti-reductionist to a certain extent, but then molecular biology changed that. It showed that if you dig down to the level of genes, then you come up against a molecule. And that's already pretty, you're getting into the quantum realm. If you ask a physicist what science do you need to describe what's happening inside a molecule, let's say, there's no questions, quantum mechanics. It's a motion of electrons and protons and that kind of stuff that's going on. If you want to understand the things that are happening inside a molecule, you've got to go to quantum mechanics. So there was that at the back of my mind, and back in reading at the end of the 20th century, I suppose, as quantum evolution was out at 2020, so it was a little bit earlier than that. And I read a book called Schrodinger's Cat by John Gribbin, and it's a great book. And I'm a popular science reader. I like reading popular science along with other stuff, but before that, I had read books about general relativity, special relativity, black holes, bending space-time, and I thought, hey, that's weird. And then I read John Gribbin's Schrodinger's Cat, and I thought, no, they're not weird. They're normal compared to quantum mechanics. That was really mind-blowing. It's, that the world down at the level of individual electrons, protons, etc., is not at all like our world. And yet our world is built of it. And that I found stunning, the idea that this different kind of world is existing at the level below which we can see it, but it's still operating all these rules that are really alien to the way we think about the world. And the kind of things that we are used to, and we consider as normal, are actually just an illusion. They're a kind of averaging up of all the weird quantum stuff. But the rules at the quantum level are very different. And at the time, we're also puzzled as a biologist, and I work on microbiology. And there was a report of a peculiar kind of mutation that was discovered by John Cairns, a very eminent microbiologist and molecular biologist who worked at MIT. I can't remember if he was working there at the time, but it was certainly very eminent and well known. And he published a paper in Nature in which he claimed that some kind of mutations become more common when they are adaptive. In other words, when they make a positive difference to the cell, then the cell will mutate in that direction at a higher rate than if there is no difference to the cell. And he did this by very detailed experiments that were described in his paper, and everyone was baffled because it goes completely against the standard neo-Darwinian dogma that natural selection, the direction of evolution is provided by natural selection, but the driving force of evolution is mutation. Mutation is random and it generates the variation, but then natural selection kicks in and provides the direction. So that's a fundamental principle of neo-Darwinian evolution. And here appeared to be the simplest bacteria were able to choose which mutations that could happen. And I was totally baffled by this, as was everyone in the field, really. It was a baffling result, and the experiments seemed sound and came from a very eminent lab and was published in a very high-profile journal, Nature. But it occurred to me that maybe, just maybe, quantum mechanics might have some explanation. because if you think about molecules and the DNA chromosome in every organism's cell is a molecule, a single molecule, it obeys quantum laws. And protons are really, the genetic code is really a code of proton position, where the protons are in the double helix. And if protons are quantum mechanical particles, then they can be in two places or more places at once. And this is one of the odd things about quantum mechanics. Objects don't necessarily have a specific position in space. They can be in multiple places at once. They can behave like a wave that's a lot of places, nearly everywhere. It can be at some probability. And thinking about that, I thought, well, maybe that's a way that cells could use this quantum indeterminacy to influence what kind of mutations happen in the cell. And I thought it was pretty crazy, and I didn't really know anything about quantum mechanics, so other than reading the book. So I got in touch with the physics department at my University of Surrey, and they said, sounds crazy, but come and give us a talk. So I went and gave a talk, which felt like, sticking my head in the lion's mouth, talking about quantum mechanics to a room full of biologists, talking about quantum mechanics to a room full of physicists. And
that is
I got a fairly
admirably ballsy. That's good. Keep going. Yeah.
Okay. And I got a fairly ballsy reception. Mostly, no, that can't be right. No, that's wrong. But Jim Al-Khalili was in the audience, a physicist, and now quite well known, but at the time not so well known. And he came up to me afterwards and said, "Look, there's lots of things wrong with what you're describing, but there's an interesting idea in there, and maybe we could work on it." And we did work on it for, I think, a year or two, and meeting up every now and again over a pint or a coffee and banging some ideas around until we got a paper out. And we wrote a paper on this idea, and then I submitted I was interested in writing science books, popular science books, because I love reading them. So I submitted a proposal to a competition in the UK at the time for popular science books, and sponsored by HarperCollins publisher. I didn't win, but I was shortlisted, and that got me a publishing contract. So I published Quantum Evolution. And so that's how I got interested in it, and that's how I got into popular science writing as well.
Well, so what I pick out of that story is that one of my passion areas is me coming to realization about 15 years ago that organisms do mutate in the direction of where they need to go before natural selection kicks in. And in fact, that's the essence of Barbara McClintock's work. And then you have a question of how can they do that? And quantum mechanics provides an explanation for how they can calculate a range of possibilities before they actually execute. Is that way of describing it compatible with the way that you think about it?
Yeah, it was. And at the time, we proposed it involved something called decoherence. Decoherence is the process by which quantum mechanical stuff becomes non-quantum mechanical, becomes classical. And that is analogous to measurement, how a quantum system is measured. It loses its quantum and chooses, if you like, randomly a particular state. But we put an idea together that this action of decoherence, that natural selection will be able to speed up or slow down decoherence depending on whether it made a difference to the cell, the mutation that we were looking at. If it didn't make a difference to the cell, that the decoherence wouldn't kick in because there was not enough of a difference between the two states, one mutated, one not. But when it makes a difference to the cell, then decoherence will kick in very fast, and that would kind of drag out the mutation out of a quantum superposition of all the kinds of possibilities that there would be. So it was very much a back of the envelope calculation and idea and theory, and we're still investigating it. Adaptive mutations has kind of up waves of interest in this idea. Some of the original experiments of John Keynes haven't been disproved in any sense, but they've been shown to be more complicated than people realized at the time. And things were happening, like cells were dying and they're releasing the DNA, other cells were picking up that DNA, and that complicates the calculations of the mutation rates. It's difficult to calculate mutation rates in non-growing cells, and that was another problem. So there were problems with this. So interest in adaptive mutations has kind of waned, although it's still there. And even in things like cancer, there seems to be some evidence that mutations may occur there are advantages for the tumor faster than you might think. So there's still something going on there. We've moved, myself and Jim, we both we're director and co-director of this quantum biology doctoral training center, and we're trying to dig deeper and more rigorously at the question by first of all looking at what is the likelihood of quantum tunneling in DNA, and recent paper from Jim's side, theoretical work has shown that the quantum tunneling could be quite prevalent in DNA. And then in experimental work in my lab, which we haven't published yet, we're finding evidence for the possibility that that there may be quantum mechanical things going on. That's as far as we'll say at the moment, as the experiments are still ongoing and the results aren't yet clear. So we're still interested in this question. But since then, there's been an explosion of interest in quantum biology with work from Greg Engel's lab, for example. Well, it was Graham Fleming's lab where Greg Engel was working, where he showed photosynthesis involves quantum mechanics, and the efficiency of photosynthesis may depend on quantum mechanics. Work with Thorsten Ritz, now at Berkeley, or was it UCLA? I can't remember now, but it might be UCLA. Has shown that avian navigation birds may fly around the world with using quantum mechanical systems of navigation. We are finding in our own lab evidence for quantum mechanical effects in things as diverse as drug activation. So there's a lot of interest, and of course enzymes. There's a lot of work from showing that enzymes work through quantum mechanical means. The protons and electrons quantum tunnel from one place to another, and that accounts for why enzymes are so darn efficient. Factors of 10 to the 20, how they speed up chemical reactions. So that involves quantum mechanics. So there's a lot of these areas now that have made the field of quantum biology almost respectable, and it's now considered not necessarily a sign of madness if you believe that quantum mechanics is involved in biology.
So Johnjoe, if you could make an appeal to, let's say you were talking to a high school graduation to a bunch of science students, and you're going to appeal for why somebody should study quantum biology instead of traditional biology, and that maybe even this could be a key to big breakthroughs in the 21st century, what would you say to that group of kids?
Well, I would say that quantum biology is right now the most interesting new science of the 21st century. It's a 21st century science. It's kind of inevitable, I believe, in the way that biochemistry, one of the drivers of 20th century biology, was an amalgam of biology and chemistry. But we know the chemistry ultimately is physics. It's If you dig down in chemistry, you come across physics. So if you dig down into the chemistry of how living things work, it's biology. And at the moment, biologists in this country and in most countries, I think, are not really aware of quantum mechanics, even never mind quantum biology. It's taught the ball and stick model of molecules, where protons and electrons have positions in space. And any physicist will tell you, no, that's just a convenient illusion, really, that a convenient teaching method, but it's not real. The protons and electrons don't have specific positions. They are wave mechanical entities. So, and it makes a difference, is what we've discovered so far. And what is really exciting to investigate is how much of a difference does it make. Alongside the areas I'm talking about, there is evidence that quantum mechanics may be involved in things like wound healing, as I mentioned, drug activation, inflammation, protein folding. So there's a lot of exciting work being done, and it's the most interdisciplinary science there is on the planet at the moment. It pulls biology together with deep physics, with mathematics, with computer science. So it's really exciting, and I don't think there's any more exciting science on the planet. And it's unlike, other areas are fascinating, like astrophysics. But how hard is it to do an experiment in astrophysics? You can do an experiment in quantum biology in your lab tomorrow. So it's something that is exciting, is kind of mind bending in a way that life depends on this weird stuff that goes against the rules that we perceive in the world, but they don't really exist, and life may depend on them. And I think that's really a kind of interesting and exciting thing to explore. And it's a bit like what I was saying about the Occam thread. You keep pulling, and more stuff will come out. And I'm sure any young scientist should throw their rod and their hook into the water of quantum biology and then pull out interesting stuff.
Well, I certainly agree with you, and I think your own partnership with Jim Al-Khalili is evidence of that. You've got a biologist and a physicist putting their heads together, drawing from multiple fields, and I kind of got sucked into this simply because John Torday and Dennis Noble asked me if I'd like to write a paper, and I said yes, not because I did understand it, because I knew I didn't, and I was kind of overdue. I knew there was a deep rabbit hole here, and so I'll certainly attest that it's fascinating. So if people want to follow you, understand what you're up to, see what you're doing, what's the best way that people can do that?
Books, obviously. Life is Simple, my most recent, Flying from the Edge, and other books. My website, johnjoemcfadden.co.uk. My other website that used to be mine, johnjoemcfadden.com, got ransomed. I haven't paid the ransom. So don't look there. Look at johnjoemcfadden, all one word, .co.uk. So you'll find a lot of stuff there, including papers that you can download, and yeah, get in touch with me.
Well, I want to thank you for your time today, and thank you for your books. I enjoyed both of these, Life is Simple, Quantum Evolution, and thanks for your time today.
Thank you, Perry. It's been great talking to you.